All right, welcome to another exciting episode of AP Chemistry here at Spain Park High School. It is Tuesday, December the 10th, 2024. And if you are enjoying these exciting videos, please feel free to subscribe to the channel and hit that like button, and even feel free to ring that bell for notifications. All right, today is Tuesday, which means that tomorrow is Wednesday. What is happening tomorrow?
Nothing.
It's actually
100% grade.
It's actually going to be a quiz. The quiz is going to consist of 5 problems. No multiple choice, no free response. 5 problems. Now, some of the problems might have an A and B.
No multiple choice.
No multiple choice.
Only free response.
Only free response.
Oh,
Only
no
problems.
multiple choice or no free response. I was like.
Only multiple choice. Oh shoot. Only problems. No multiple choice. Yeah. No. Only problems. 5 problems. The 5 problems are going to be these types of problems. These are going to be your key words. When we have a calorimeter, we're going to look at a calorimeter problem. Okay? But whenever you see the word calorimeter, okay, you're going to use Q loss equals negative Q gain. Heats of formation, that's the ones where we look up the answers in the back of the book. Those values are always given to you. You do not have to memorize that chart of heat of formations by tomorrow. So the values are always given, but the key phrase is you're mentioning heats of formation is given in the problem. That's going to tell you that you're going to want to use this equation. In the notes that I'm going to give you when we come back from Christmas, which are given, there's somebody else's notes that from online, they refer to this equation as the Big Mama equation. Okay, because this is the one we use. This is the one where you just look up stuff in the back. And then, products minus reactants. Hess's law is what our lab was kind of about. Hess's law was when you have multiple equations, your delta H's are summative. We add them together. We can flip, we have to know what to do with the signs if we flip them and that kind of thing. Okay? This is what we're going to learn how to do today using bond enthalpies. The key word here is bond enthalpy. Bond enthalpy, another way of saying that is bond energies. How much energy does it take to break a bond? Now, what makes this one different, and we're gonna spend time talking about this today, is that where are bonds broken as reactants or products? In a chemical reaction, where are bonds broken as reactants or products? If you're going from A plus B going to C plus D, what do you have to do first before you can get to C and D? It's not supposed to be a hard question.
Break the bonds.
Break the bonds in the reactants. Okay? Well, I know, but everybody else is looking at me like a deer, like a cow looking at a new gate. Like, when'd that get here? Just like, okay? Just kind of that look. So, reactants, this is reactants minus products. This is the one that's backwards from all the other ones, and especially when we get to delta S and delta G as soon as we come back from Christmas. And that's when we're going to take the big test over all of this, is after we include. And we haven't done any practice AP problems because most of them incorporate delta H with the delta S and the delta G. And so I don't want to just kind of do partial problems. So we'll wait. When we come back, we'll integrate all of this in and then just kind of practice, we'll review this, and then come back and put the whole thing together. All right? But we're already a little bit ahead of the game, so we'll take time just to get this. So, but again, we'll focus on this in a bit. And then the stoichiometry. The stoichiometry to me just means using kilojoules per mole. And we've already done kind of problems where they give you the delta H of the reaction, and then they say how much heat will be released if 10 grams of this reacts. And you just change grams to moles and then use the kilojoules per mole. Okay? This is what a lot of those practice problems that you did in class the day I wasn't here, you did a lot with the stoichiometry. That's just using kilojoules per mole, the heat of the reaction, as a conversion factor. Okay, and even in your lab that you did, you did that kind of changing everything to moles and using that. Okay, so this is what the quiz is going to be about. So I want to do just a couple of practice problems with the calorimeter more, and then I'll come back and we'll talk about how to do these problems, and then we'll be done for the semester until we take the quiz and then take a small, easy semester exam. That
Only 1,000 free response questions.
only 6 pages worth.
Is it easy
Only
now?
6 pages. But you were like A, B, C, D.
All right, so if we look at a simple coffee cup calorimeter, one type of reaction, and those of you that had me last year, we did this in class. I did it as a demonstration in class. We did it as an in-class lab for Chemistry 1. But if we have a piece of this metal, let's just say iron in here, and it's in water that we're heating up, and the water begins to boil. Okay? Steam's coming off. So what temperature is that water? 100 degrees. So I know that this is 100-degree water. Okay? So then, and this is attached to a string. And so over here, I have my coffee cup calorimeter. And in the coffee cup calorimeter, I have 100 grams of water. And it is at 20 degrees Celsius. Okay? My iron, the mass of my iron is 25 grams. Okay, I weighed that out before I put it in the water. I have a string attached to it. So I have 25 gram piece of iron attached to a string in 100-degree water. And then over here I have my coffee cup calorimeter where I have 20-degree water and 100 grams of 20-degree water. So now I'm going to take this out. Okay, I'm going to take this out and transfer it into here. Well, let's just say this, Fe. And I'm going to put it into here. So now I have my Fe in here. Okay, so I'm going to quickly take this out and just put it into there. What's going to happen?
The heat's gonna go from the iron to the water.
Okay, the heat's going to go from the iron to the water. So what's going to happen to the iron?
It's colder or looser.
It's going to cool down. What's going to happen to the water?
It's gonna get hotter.
Until when?
They're in equilibrium.
Thermal equilibrium, which is a fancy way of saying
The same heat.
not the same heat, same
Temperature.
temperature. Okay? So the iron is hot, the water is cold, the heat's going to transfer. So what equation? I'm using a coffee cup calorimeter, so what equation do I know I want to use?
Q loss equals negative Q gain.
That's a lousy Q. Q lost is equal to negative Q gain. So in this case, what's losing the heat?
Iron.
The iron. So this is going to be the Q of the iron is going to equal the negative the Q of the water. Okay, now I'm just being overly, but just making sure that we see that. So now, the iron, they're not reacting with one another. How do I calculate the Q of the iron? Oh, the goal of this is, that might be important. What is the specific heat of Fe? Now we need one other piece of information in order to be able to do this. What do you think that other piece of information is?
Joules. Something to.
Not yet.
Final temperature of the water.
Final temperature of the water. So let's just say that we have a thermometer in here, okay? This is my thermometer. I'm such the artist, okay? And we're gonna say that T final is equal to 23.4 degrees Celsius. Now I'm just making this number up so that it's probably not gonna come out to the right value for the heat of, specific heat of iron, but this is how you would calculate. Does anybody remember us doing that last year? Okay, I had the boiling water up here on the thread, and I just took the metal, put it into the coffee cup calorimeter. Okay? So how do I calculate the Q of iron? How do you calculate Q? MCAP. So it's going to be the mass of the iron times specific heat of the iron times the change in temperature of the iron is equal to the negative mass of the water, specific heat of the water, change in temperature of the water. So we have 6 variables. We should be able to know 5 of them. What's the mass of the water? Pardon me, mass of the iron?
25.
25 grams. Specific heat is what we're looking for. What's the change in temperature always? What minus what?
Final minus initial.
Final minus initial, always. And this is real important on this type of problem, so we get the signs right. Okay, so the final temperature is 23.4 degrees minus my initial temperature of the iron, which was 100 degrees. No, I don't need that bracket. Is equal to the negative, the mass of the water is 100 grams. What's the specific heat of water?
4.184.
Now that's actually always going to be given to you. And then the change in temperature of this one is going to be 23.4 degrees Celsius minus the 20 degrees Celsius. So all of this inside the bracket, what is that? Relate that to the lab yesterday, that we worked on yesterday. What is inside the bracket? What is that?
What was absorbed?
By
The
calorimeter, or more simply, the water in the calorimeter, right? So what's the sign going to be of everything in the bracket?
Positive.
Positive. Because it's absorbing the energy. So we're assuming that all of the heat lost by the iron is absorbed by the water. Okay? Nothing's lost to the surroundings. Okay? No heat lost. It's all the heat that's lost from the iron. So we just put the negative, because this one needs to equal the positive of this. It should be the negative of that. So now you just do the math. Now it's going to be easier, easier mathematically if, first off, we get delta T. What's this delta T? This is going to equal 76.6. Negative 76.6 degrees Celsius. So then when you multiply that by 25, what do we get?
Negative 1,915.
Say it loud enough for an old man to hear.
Negative 1,915.
915. And now notice that that's grams and degrees Celsius, nothing cancel. So that's grams times degrees Celsius, okay, times the specific heat of iron is equal to, okay, and then just multiply all this out, but this is going to be 3.4 degrees Celsius, okay? So what is all of this going to equal? Negative what?
Negative 1422.56.
0.56? Okay, and now grams cancel, degrees Celsius cancel, so we're left with joules over here. So then obviously, what are we going to do? Divide by the 1915, negative, grams, degrees Celsius. So notice that none of your units cancel. So the specific heat of iron, according to our calculations, is going to be
0.7429.
okay, so 3 sig figs, let's just say.
0.743.
And notice joules per gram, degrees Celsius. Now the reality is that when you look up the specific heat of iron, it's like 0.441. I think it's something like that. Specific heat of iron. 0.449. Okay? So we're still over. So what number do you think is wrong?
T final.
Say it again?
T final.
T final. Because that's the only one I made up. Everything else is pretty, I mean, we could be consistent. I can control 100 degrees. I can control 20-degree water here. It's just how much is the temperature going to change, I just guessed. Okay? So how should I change this to make it work? What would I need to do with the T final? Do I need to make it bigger or smaller?
Bigger.
Look at the math here. Now, when I'm dividing here, I need this number to be smaller, right? So what does that mean about this number? It needs to be bigger. And what about this number? It needs to be smaller. So how do I do that? How do I make this number bigger? Make T final smaller, because that's going to make this difference bigger. So even 3 degrees is too much for the water to come up, thinking that you're putting 100 degree iron into 20 degree water, but it's only going to raise it less than 3 degrees. Okay? So somewhere along the line that temperature's there. And then notice also, if I make this one smaller, that this number is going to be smaller in the numerator as well. So this is going to be smaller, this one's going to be bigger. Both are going to combine to make this a smaller number. So obviously the temperature change here is too much. It's probably closer to 22 degrees. Okay? Why such a big difference? Why does water only go up a little bit and the iron comes down so much? There's more water, 4 times more water. That's one reason.
The specific heat.
The specific heat, 0.449 versus 4.184. Almost 10 times larger specific heat for water. What does that mean? It takes a whole lot more energy to raise the water in temperature than it does the iron. So the iron just isn't holding to get it to 100 degrees. It just doesn't hold that much energy inside of it. So when you put it into the water, there's not that much energy to release back out to it. 10 times almost less energy than what it was for the water. So the specific heat, so just always remember, the larger the specific heat, the smaller the change in temperature. It's always how much does a change in temperature cost, okay? So I want to just kind of let you have a practice on this. So there's a problem in a different textbook, just so you can kind of do one of these. It's not just like this one, but it's similar. I don't have my glasses on. I think it's number 55 right here. Oh, I don't even have power on. I think while that's coming out. Look at number 55. This 30 grams of water at 280 K is mixed with 50 grams of water at 330. Calculate the final temperature of the mixture, assuming no heat loss. So let's take 5 minutes or so and see if you can do this. Go ahead and pause the video. You can pause it. All right. So again, is mixed, they're mixed, calculate the final temperature of the mixture, assuming no heat is lost to the surroundings. So you're mixing, you're assuming you're in an insulated container, you're putting hot with cold. So I know that what equation do I want to use? Q lost is equal, this is 55. Q lost, I'm going to equal my negative Q gain. Now what's losing the heat?
330.
The hotter water, right? The 330 K is losing and the 280 K is going to gain. So I'm going to have the mass, and I'm not going to break it up on this one. The mass is 50 grams of the hot water. The specific heat is the same, 4.184 joules per gram degree Celsius. Actually, we'll just say joules per gram K. Times the change in temperature, which is going to be T final minus my initial temperature, which is 330 K, is equal to the negative of the gain, which is going to be the mass of the 30 grams times 4.184 joules per gram K, times my T final minus 280 K. So your T final is going to be the same for both substances. Now, before we even get the answer, does your answer make sense? Is it going to mean there's 25 degrees difference, or there's 50 degrees difference? Is it going to meet right at 25? Is it going to meet? Does it come out to 305 K? Why not?
There's more water substance.
Because there's more water. So we know that our answer, just as from a logical point of view, needs to be closer to the 330 than it is the 280. It's going to be above 305. That's the midpoint, right? Just common sense. So if this were like a multiple choice type question, you could then just kind of pick and choose your answers without even having to do some of the math, knowing that it's got to be somewhere more than the 25 midpoint. So you can eliminate answers below that just out of common sense. All right, so when you go through, I'm assuming you can all do the algebra. So you got your T final is equal to 311.25, but let's just say 311K. We good with that? So when you're putting hot with cold, they're not really mixing. It's not a chemical reaction. So you're just going to use Q loss equals Q. You're going to use MCAT on both sides of the equation. Now notice again, when we did the styrofoam cup, we did not add the 25 grams in to the 100 grams. Here, the cold water and the hot water, okay, we didn't add their masses together. The only time you're going to add the mass in is like in our lab when you're dissolving something and it becomes part of the solution. Okay, that's the only time that's going to be part of this mass over here, is when you dissolve something and looking at the heat of solution like that. Okay? Does anybody have any questions on that? So we need to be able to do calorimetry problems. All right, let's look at our fifth and final type of problem. And it's all going to involve these things called the enthalpy of a reaction. This is number 5. Using the Bond Enthalpies. Which we can call bond energies. Remember, enthalpy and energy are interchangeable, bond energies. To calculate delta H. Now, in this problem, we're going to use the delta H of a reaction is equal to the sum of your bond enthalpies broken minus the sum of bond enthalpies formed. Now we already kind of said this, but where are bonds broken? Reactants or products? Reactants. So this is your reactants. These are your products. Now again, two things that make this more confusing. Number one, all of the everything that we do in thermo is products minus reactants, except this one. Secondly, all the other equations are given on the equation sheet, but this one's not. Okay? But your key phrase, your key words, do you know to use this when they're giving you bond enthalpies? But this is gonna be really straightforward because the information is all gonna be given. So if you turn in your books to page 327, pardon me, 337, you look at page 337. We can look at problem number 69. Using the table 8.4. Now, 8.4 is on page 326. So turn to page 3, keep that open, but turn to page 326 at the same time. Okay, so page 326 gives you a table of all of the different energies it takes to break a carbon-carbon single bond, a carbon-carbon double bond, oxygen to oxygen single bond, and oxygen to oxygen double bond. Those are your bond energies. Now, so we have this chemical reaction. Now remember, enthalpy, bond energy, is a state function. What does that mean again? State function. Remember my example of driving from here to Denver? When mileage, it depends upon the route you're going to take. But the change in elevation, it doesn't matter how you get from point A to point B, the change in elevation is going to be the same. Okay? A state function is like the change in elevation. It doesn't matter how you get from point A to point B. So we're going to assume on these is that you're going to break every single bond here, and then you're going to reform them here. It's going to require energy to break all these bonds. It's going to release energy to form all these bonds. The difference between the two is how much energy is left over or consumed in the reaction, the delta H. Okay? Now the reality is in the reaction, it's not really going to do that. Some of them are breaking, some of them are forming, but again, it doesn't matter how you get from point A to point B, so this is just a different way of calculating delta H. We could use your delta H of formations. We could use this equation to calculate this and use the internal energy of the whole thing if we knew the heat of formation of all of these. But again, we're just using a different methodology. And so when we look at this, then I'm saying I want to use this equation here. So if I want to use this, I want to say, okay, well, what bonds are broken and what bonds are formed? Well, okay, you all have this equation written, right? So my delta H here of the reaction is going to equal the sum of everything broken. Well, what do I need to break here? I've got to break this bond, I got to break that 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 one, I got to break that one, I got to break that one, and I got to break that one. Okay? So I'm going to say, how many carbon to hydrogen bonds do I have to break? 4. So I'm going to say 4 carbon to hydrogen bonds plus 1 carbon to carbon double bond plus 2 OH bonds plus 1 oxygen to oxygen bond minus how many bonds are going to form? Well, I'm going to have 4 carbon to hydrogen bonds again. I'm going to have 1 carbon to carbon bond. I'm going to have 2 carbon to oxygen bonds plus 2 oxygen to hydrogen bonds. Did I get them all? This bond, these 4, the carbon, okay? So you got to have the Lewis dot structure in order to be able to do these. To really be, now, supposedly know how to draw Lewis dot structures, but almost always on the AP test, they give you the Lewis dot structure if you have to do this. On the quiz tomorrow, you have the Lewis dot structure already given to you. You just have to be able to do this. So, and you have obviously all the values there that are given on page 326. So, delta H of the reaction is going to equal 4 times, what's the carbon to hydrogen bond order? Bond strength, I mean, bond energy. Carbon to hydrogen. 413. Plus 1, what's the carbon to carbon double bond? 614. These are all kilojoules. It's kilojoules per mole on the table, but we're multiplying by how many moles we're breaking. So it's really turning out to be kilojoules, just for the record, as far as units. Plus 2 times OH. What's OH?
463.
463. Plus 1 times the oxygen to oxygen.
146.
146. Notice that that one is very small. An oxygen to oxygen single bond, that's a peroxide. Highly unstable, doesn't take much energy to break that bond. 146 compared to all these other values is much, much less. Peroxides are very easily broken down. Minus 4 times that carbon to hydrogen again, 413, plus 1 times carbon to carbon. What's the carbon to carbon one?
348.
348. Plus 2 times the carbon to oxygen, which is 358. Loud enough for an old man to hear.
358.
Okay. Plus 2 times, and we already have the OH, 463. So now we can make the math a little bit easier. What cancels out?
The 2 413s.
The 2 413s.
And then the 2 463s.
2 times 463. So then it's just going to be the 614 plus 146. It's going to equal 760 minus that side. So what does it all come out to?
Negative 304 kilojoules per mole.
Okay, so it's just bonds broken minus bonds formed. Again, everything's given to you. You just plug into the equation. You just have to be able to keep track of what bonds are formed and which ones are broken. Okay? You'll be given the Lewis dot structure. The key is how do I know to use this? So you look at the word, when you're given bond enthalpies, bond energies, that's your clue, context clue, that I'm going to use this. Again, every single one of these equations are pretty straightforward. Pretty easy to use in and of themselves. The problem is, how do I know which one to use? You got to look at the context clues in the problem, and they tell you which equation you're going to have to use. Okay, that's the part that you have to just quote study or get into your head, because all of these equations, this one's given. I don't think Q lost it, but Q equals MCAT I think is given on the equation sheet. Okay, this one's not, and then Hess's law. Those aren't actual equations to plug in. So right now, go ahead and try to just do B as a practice. Go ahead and pause the video. All right, so when we go through and do this, let's just set it up. I mean, I think most of y'all pretty much got this, but bonds broken, we're gonna go, how many carbon to hydrogen bonds do I have to break? 4 here, but there's another one over here, right? It's gonna be all the same, it doesn't matter what it is. So we can say 5 carbon to hydrogen bonds, okay? Then we're gonna be 1 carbon to carbon double bond, plus 1 carbon to nitrogen triple bond, minus, okay, nice again, 5 carbon to hydrogen bonds, plus 2 carbon to carbon bonds, plus 1 carbon to nitrogen triple bond. Now, is anything, before we even plug in numbers, what's going to cancel?
The 5 carbon hydrogen.
That's going to cancel with that.
And the.
That's going to cancel with that. So the reality is we just need the carbon to carbon double bond, which is going to equal how much?
614.
614. So it's 1 times 614 minus 2 times, well actually we don't even need to put the bracket, minus 2 times, what's the carbon to carbon?
348.
348. And that's going to equal
Negative 82.
negative 82 kilojoules. Okay? So again, pretty straightforward. Not too hard. Does anybody have any questions on that one? We're good? Okay, so that's all that's going to be on the quiz. 5 problems. Just kind of going through, doing the problems, just being able to apply these principles on these different types of practice problems that we've done. I will tell you this, that there will, I'm just getting out of the way so they can see that. There will be a lab type question from yesterday. Okay, so you need to make sure you got to do the lab, and the labs will be due tomorrow. I'm going to collect the labs tomorrow as well. Okay? Any questions on any of this? We're ready? All right, well, you can have the rest of the time today to do whatever you need to do, and go Jags. That's the clue to stop it.
Give it a thumbs up.
Oh, give it a thumbs up, huh?
Yeah.